Hello, Algebra 2. I just wanted to take a few minutes to start you guys off on practicing graphing, but then also knowing what it means to solve by graphing. So we're going to bring together a couple different things today. I am going to ask you guys to pause your video a couple times so that you can actually graph some of these functions. So I'm starting off in vertex form, and vertex form is when you guys have the parentheses, like this one does, and the square on the outside of the parentheses, because you know that your vertex comes from this -2 and this -4. So I know that my vertex is at a +2 and a -4, which means my axis of symmetry is at 2, and that helps me graph it because I can go to +2, -4, just here, and I know that I'm going to use my pattern or maybe my calculator to help me graph. So I'm going to do 1 over, 1 up, and then 2 over and 4 up. Oops, we got to count one more. And then I can connect my dots. So 2 over, 1, 2, 3, 4 up. And again, these are the same points that you guys would find if you used your calculator to graph. So there's my parabola, and it looks something like that. And then I can do the same thing with the second one, because I know that I have this -1 here, +2 on the outside of the parentheses. So my vertex winds up being the opposite of what's on the inside of the parentheses. The 2 comes from the outside. That means my axis of symmetry is -1, and I can graph it. So I'm at -1, +2, and then I'm opening down because of this minus sign in front. That is a reflection. So that means I'm going to go down 1 and to the left 1 and to the right 1. And I'm also going to go out 2 and then down 1, 2, 3, 4. And there is my curve opening downwards. My smartboard marker got a little bit off. But then also remember, guys, your axis of symmetry goes directly through the middle of my graph. So I know that I can fold both halves of my graph and they would match up. So this one on the first one, that's the line of x equals 2, because that's what my axis of symmetry is. So it's right at where x is 2. And then for this one, it's x equals -1, and that is because of that axis of symmetry right there. It's the same point. The axis of symmetry goes through your vertex. So it's that same x value as your vertex. This is what you guys were doing last class, so I'm going to take you guys a step further. That was vertex form. This one is quadratic function in standard form. And the only difference is that you guys FOIL it out. So if you look back at the last ones that we just did, notice how these are being squared, right? So if I actually FOILed them out, so let's say I take number 2 here, negative, and then I have x plus 1, multiplied by x plus 1, and then I have this plus 2. Well, if I FOIL that, I'm going to get the x squared plus 2x plus 1, and then I have the plus 2 on the outside. I'm going to distribute my negatives, so I have -x squared minus 2x minus 1, and then I continue to simplify, and I get -x squared minus 2x plus 1. Once I FOIL, I get the same exact function. It's going to look the same when I graph it, but the equation looks different. It doesn't have the parentheses with the squared part on the outside anymore. Now it's just a polynomial. So that's what changes it from vertex form to what we're about to talk about, which is standard form. So in standard form, you have an a value. You have the a value multiplied by x squared. That's what makes it quadratic. Then you have the b value, which is the middle term. That's the coefficient for the middle term, multiplied by x. And then plus c, that is your constant term at the end that doesn't multiply by an x. So the ax squared, that whole first term, that's what really makes this a quadratic function. That's what makes it look like a u shape. If I didn't have that x squared term, if I just had the bx term, that is what, I'm going to use green for that one, that is when I would have a linear function. And then if I only had the constant at the end, so let's say I took away the x squared and the x term, that would just be a constant function, which looks like a horizontal line, whereas a linear function could be a positive or negative slope, depending on what that b value is. So we're basically just adding on to our linear function that we started with, and now we're making it quadratic. Some examples of what you guys might see. Let's say you guys were given 2x squared minus x plus 5. My a value would be the 2. My b value would be the negative 1, because that's multiplied by x. And then my constant would be 5. Let me say we were given negative 3x squared plus 7. Well, that's quadratic because it has this x squared piece to it. The a value is negative 3, but I don't have a b value. If I don't have a b value, my b value is 0 because it's missing. 7 is my constant for that one. And then let's say I have 7x squared plus 2x minus 1. Same thing, my a value would be 7, my b value would be 2, and my c value would be negative 1. Remember that our a value in all of these terms, these are my a's, that corresponds to the a value that's in the vertex form. When you guys graph, the a value always tells you whether your function is going to, your picture is going to look like it's upwards or downwards, because that's what reflects it. And then it also tells you the stretch. Is it stretched or is it compressed? Does it look wider or skinnier? That a value still matters because it's going to tell you the same thing that it would in vertex or in standard form. So let's try a few examples of standard form equations. The first one is the function x squared minus 4x plus 4. Go ahead and pause the video here so you can graph this in your calculator and then translate the points from your calculator onto the diagram that I have for you. You should get a picture like this, and from the diagram, or from the picture that you guys drew, you should be able to answer that our vertex, I'll use a different color for that, the vertex right in the middle is at the point 2, 0. That means our axis of symmetry is at 2, so that is a vertical line at 2, so that's x equals 2. Solutions, roots, zeros, we've been talking about these throughout the year. Solution is when you have an x-intercept. That's another way to write it, x-intercept. So in our picture, that happens, oops, there we go. That happens at 2, so it happens at 2, 0, right there. My domain, again, my left arrow is going up and left, my right arrow is going up and right. So I actually go all the way to the left and all the way to the right, so I cover all x values from negative infinity to positive infinity. My range, though, the lowest I go is right here. That number is 0, right? I don't go below that x-axis. So my range is my y values. The lowest I go is 0, and I include 0 as my point. Oh boy, I can do better than that. Let's try that. There we go. And then I can go all the way up to infinity. Perfect. End behavior. Remember the nice way we wrote end behavior last time? We said as x goes to the left, so negative infinity, where is the y value going? And my tail, the tail end where the arrow is going up to infinity. And as x is going to the right, positive infinity, my f of x, or my y value, is also going up to infinity. So that is example number 1. Example number 2, go ahead and pause the computer now so that you guys can take a moment to graph this and see what it looks like. For this diagram, you guys should get a graph that looks something like this. Now let's look already back over here. You guys were given this function equal to 0. This function really is negative x squared plus 4x minus 6. We set it equal to 0 because this question is asking us to solve what x is when our function equals 0. So in other words, when y is 0. this is really asking this question right here. What are the solutions, the roots, or the zeros? So those are slight differences in how your question is going to be asked. If it's f of x equals, then it's just giving you the function. If they set it equal to 0, they want to know what the 0 is. So it would be part D on this sheet. Also, guys, notice that your a value is negative because it's a -1 there at the beginning, right in front of the x squared. So your coefficient is -1, which means our parabola should open downwards, and it does. So that matches very well. So we have a graph. We have a vertex is at +2, -2. The axis of symmetry goes directly down the middle. It is a vertical line at 2, so x equals 2. And take a look at the blue graph that we drew. Does it actually cross the x-axis anywhere? It actually doesn't. So since it doesn't, there's actually no solution for this graph because there's no point where that would satisfy the function actually equaling 0. My domain, again, is -infinity to +infinity. My range, because it goes downward, I start at -infinity, and I come all the way up to -2, which I want to include. And then I'm going to write my end behavior as x goes to -infinity. So when I look to the left, the y value also goes to -infinity. And then when you look to the right of the graph, when x travels out to the right, your y value, f of x, also goes down. There we go. All right, we're going to do one more example together. Go ahead and pause the computer one last time so that you guys can graph this one. And I'll start you guys off with a little hint. Right now, you're given x squared minus 2x equals 3. Again, because there's no f of x here, they've actually made your f of x 0. So they're trying to make this equal to 0. If I want to make this equal to 0, I have to move this 3 over to the other side. So 3 minus 3, I'm left with 0 on the right-hand side. And then I have x squared minus 2x minus 3. Now I can graph it because the function is f of x equals x squared minus 2x minus 3. I can now graph it as a quadratic function and make it look like a parabola because of what I was given here. I could use my calculator to solve it before I graph it like this, and we'll talk about that when we do our calculator day. We're going to learn how to do all this on the calculator as well. Right now, we're just graphing these quadratic functions and trying to figure out the different aspects we know. So go ahead and graph this function, x squared minus 2x minus 3. I had to move the 3 over because I want every term on the same side. So pause your computer here and go ahead and graph. So the function you get with this looks like a parabola that has been moved downwards, away from the origin. It moved down and it moved to the right. Down 1, 2, 3, 4 units, and then right 1 unit. So I have my graph. I have my vertex. My vertex is at +1, and then 1, 2, 3, -4. My axis of symmetry goes directly down the middle of the graph, so x equals 1. My solutions, this is where I want to look. Where does the graph cross the x-axis? It crosses twice. It crosses at -1, 0, and it crosses at +1, 2, 3, 0. My domain, again, for all parabolas is -infinity to +infinity. My range begins at 1, 2, 3, -4, right down here. So at -4 is where this begins, and we go all the way up to infinity. And then, of course, as x goes to the left, so to -infinity, my y value goes upwards. And then if I look to the right of my graph, so when x goes to +infinity, f of x also goes up. So just to recap, if you guys draw a quadratic function and it crosses twice, you'll have 2 solutions. If it crosses not at all, you have 0 solutions. And if it hits once, you'll have 1 solution. See you tomorrow.